today we will first look into another example of grammar from which we can make transition diagrams for predictive parsing. So, the grammar that we consider is like this, that it is similar to that expression grammar. So, that expression produces term and expression tail, where expression tail is plus, then term, then expression tail or epsilon. So, it is similar to that ETF grammar, where we have eliminated that left recursion and we are writing it in explicitly. So, E dash we are writing like expression tail, then T dash we are writing it as factor term tail or factor tail, like that. So, this term produces term or followed by factor tail, and factor tail is star factor, then term tail or epsilon, and factor produces within bracket expression or ID. So, the transition diagrams that we make is like this, that first we have got this for the expression. So, it is state 0, from there it goes on term, it goes to state 1, and from there on expression tail it will go to state 2, and state 2 is a final state. Then this expression tail, so expression tail produces plus term, then expression tail epsilon or epsilon. So, it is like this, that expression tail, so it is starting at state 3. So, on plus it will go to state 4, and then on term it will come to state 5, and from 5 on expression tail it will go to 6, and there is an epsilon production. So, from 3 on epsilon it will go to state 6. Similarly, term produces term and then factor tail. So, it is represented like this. So, then this factor tail producing star factor term tail. So, it is term tail producing that is basically this is this should be actually factor tail. This should be factor tail. So, this is producing like this, the term tail producing star factor and term tail. So, this way this whole expression is made, and this factor produces within bracket expression and ID. So, with bracket start expression, then bracket close or this is ID. Now, we can simplify this expression, this set of transition diagrams by like this. For example, this expression tail, we can eliminate the self recursion, like here you see in the expression tail. So, it is calling the routine expression tail again. So, instead of that, from 5 we can come back to state 3. So, that is done here from 5 on epsilon. So, it comes back to state 3. So, that is calling the expression tail. So, by this way we can simplify the diagram a bit. We can remove the redundant epsilon edges, like this is a redundant epsilon edge. So, we can altogether remove this state 5, and from state 4 on getting term I can come to state 3. So, that is possible. Similarly, from then if we substitute this expression tail into the diagram for expression. So, in the diagram of expression was like this, there we had expression tail. Now, we have modified the expression tail. So, we just substitute that expression tail diagram there. So, this is giving us expression this is giving us that this term, then this expression tail diagram is substituted. So, it is like this. After that you can simplify, like say from here on term it is going from 0 to 3, and then on plus and term it is coming back to state 3. So, instead of that, on plus I can take it back to state 0. So, it is done like this, and then on epsilon it goes to state 6. So, that way we can simplify the expression, these diagrams. So, this is the final set of diagrams where we have got in the diagrams for expression, term and factor, where we have substituted and eliminated the redundant edges and states, and this is the final set of states. So, we can use these diagrams for purpose of predictive parsing. So, as we have seen in the last class, so we can do a simulation, and then we can see whether a given string is acceptable by the set of diagrams. Next, we were discussing on this first and follow computations, because we want to have a non-recursive version of this predictive parsing. So, the first computation we have seen in the last class, where we said that so if I have got a general production rule like this, x producing y1, y2 up to yk, then so this whatever is in first of y1 will be in first of x accepting epsilon, and then whatever, so if first of y1 contains epsilon, then whatever is in first of y2 accepting epsilon will also be in first of x. And so if all of them have got epsilon in their first y1 to yk, then only epsilon will be there in the first of x. So this way we can compute the first set, and we have seen an example in the last class that shows us how to compute the first set. So today we will next look into the computation of follow. So follow means the terminal symbols that can follow a particular non-terminal in any sentential form. So sentential form, we say that, okay, starting with the start symbol of the grammar. So if you try to derive strings, then all if you think about all possible strings of terminals and non-terminals that can be derived from the start symbol of S, then in any of those strings, if a terminal symbol appears after a non-terminal symbol, then we say that the follow set of the non-terminal symbol will have this terminal symbol. So a typical, so the rule, you can understand that the rule that we are going to follow, like if this is a production rule, A producing alpha, B beta, then whatever I can derive from beta and whatever be the first of that, so that those symbols will be following B. For example, if first of beta contains the symbols say small a and small b, then small a and small b will be in the follow of B. So accepting epsilon, of course, epsilon we cannot take because maybe the actual string that we have is alpha, b, beta, then some gamma, etc. So even if this gives me epsilon, so this first of gamma whatever symbols are there will be coming to the follow of B. So this way we can compute the follow of B. So whenever you have got a rule like this, A producing alpha, B beta, so whatever is in first of beta will be in the follow set of A. So that is one rule. The other rule that we have is if there is a production A producing alpha B or A producing alpha B beta. So I will come to this part later. Consider this rule, A producing alpha B. Then where then everything in follow of A will be in follow of B. Why? Suppose starting with the start symbol of the grammar, we are deriving strings at some point of time I have got a string where say this is say A1. So these symbols are there, these terminal and non-terminal symbols are there. Okay. Say after some time there is one A, and after that I have got a symbol say small a. Okay. Then in the next production what I can do, so this A may be replaced by alpha B. So what can happen is that this string will get transformed into something like this. So this is alpha B A. So that means if A can come in the follow of capital A, if small a can come in the follow of capital A, then small a will also come in the follow of capital B. That is obvious, because in the next stage I can replace this A by alpha B. So whatever symbol was following A will now follow B. So this is so that is the first part. Okay. Now if the rule is slightly complex, like instead of being alpha B, if the rule is alpha B beta, in that case, so what are the symbols in follow of B? So whatever is in first of beta is in follow of B, that we have seen in this rule. Also if this first of beta contains epsilon, if first of beta contains epsilon, then what will happen is at say from this I can rewrite this as A1, A2, then capital A1, capital A2, then B1, etc. And then this A can be replaced by alpha, B, beta, then small a, and it can go like this. Now if first of beta contains epsilon, that means from this this beta through some derivational steps, this beta can be replaced by epsilon, so that the string gets transformed into something like this: A1, A2, capital A1, capital A2, B1, then alpha b, this beta part reduces to epsilon. So, A comes immediately. So, that can happen. So, actually these two rules are similar. If we say that the first of beta contains epsilon, then these two rules are similar. So, naturally I can whatever is in follow of A will be in follow of B. So, that is the second rule. So, these are the three rules and so for the start symbol of the grammar there is a special rule that dollar will be in the follow of S. So, using these three rules, so we will be able to construct the follow set. So, let us take some example and try to see like how this follow computation can be done. Say for this grammar. Now, for this grammar, so applying the first rule that says that the if something is the start symbol of the grammar, then dollar will be in the follow set of E. Now, start symbol of the grammar is E. So, the dollar will be in the follow set of E. So, dollar is included. Now, you scan through this grammar, try to apply the first try to apply the rule that whenever we have got A producing alpha b beta, then whatever is in first of beta is in follow of B. So, if we try to apply this, so apply to the first rule. So, alpha is epsilon, B is T and beta is E dash. So, whatever is in first of E dash can be in the follow of T. So, first of E dash is already computed plus and epsilon. So, out of that epsilon I will not take. So, this plus will go to the follow of T. So, follow of T has got the plus symbol. Then by applying, so second rule also if we try to apply that first principle alpha b beta. So, alpha is plus, B is T and beta is E dash. So, so this does not add anything. So, it remains as it is. Then if we apply this rule, then whatever is in first of T dash will be in the follow of A. So, first of T dash has got star and epsilon. So, follow of F. So, follow set of F has got star there. From this rule nothing new comes, because whatever is in follow of T dash will be in the first of T dash will be in the follow of F. So, that we have already done. And here you see if we apply this rule, so alpha b beta. So, this is alpha, this is B and this is beta. So, whatever is in first of beta is in follow of E. So, first of beta, that is close parenthesis. So, first of it contains close parenthesis only. So, in the follow of E we will have close parenthesis. So, follow of E has got close parenthesis there. Now we will apply the second rule. So, whenever we have got A producing alpha B, then whatever is in follow of A is in follow of B. So, whatever is in, so follow of E will be in follow of E dash by this rule. Whatever is in follow of E will be in the follow of E dash. So, follow of E dash, follow of E has got say close parenthesis and dollar. So, they will be added to the follow of E dash. So, close parenthesis and dollar are added here. Similarly, if you apply this rule, so E dash producing plus T E dash, where first of E dash contains epsilon. So, by the second rule applies for the follow set, and then this whatever is in follow of E dash will be in the follow of T. So, follow of E dash has got close parenthesis and dollar. So, close parenthesis and dollar, so they are added to the follow of T. So, coming to the third rule, so whatever is in follow of T will be in follow of T dash. So, follow of T has got plus close parenthesis and dollar. So, they are added to the follow of T. Okay, or follow of T dash. So, follow of T dash has got plus close parenthesis and dollar. So, this way we have to go on applying the rules again and again till the follow sets do not change. So, it is slightly involved, the process is slightly involved, because you have you really do not know like when you are going to terminate. So, you have to go on trying the three rules that we have listed for follow computation, and whichever rules so when there is no more addition to any of the follow sets, then only the computation will terminate. So, this way it becomes a bit difficult to compute the follow set, but you can very easily write a computer program and for doing this thing iteratively till we are coming to the all the sets they have got their maximum possible entries in them. So, this way we can compute the first and follow sets. So, once we have computed the first and follow sets, we can go for constructing the parser for this predictive parser, which is a non-recursive version, and they are known as LL1 grammar. So, this type of so as I said that this it is left to right the first L. So, there are two L's here, the first L will mean that the parser will take a left to right scan of the input, and the second L means it will produce a leftmost derivation. So, it will the parser or the compiler that will be designed based on LL1 strategy. So, it will be scanning the input from left to right and it will produce a leftmost derivation of the input string. And in general we have got LLK. So, this in this particular case k is equal to 1, that will tell how many symbol look ahead we use for parser to proceed. So, look ahead means that at present so we are looking at the current symbol. So, if it is looking only at the current symbol, then we will be calling it LL1 grammar or LL1 parser. Now, if we see that so now the decision is taken based on the current symbol only. So, if you need to check k more symbols ahead to take a decision, okay, in that case the parser will be called an LLK parser. So, the grammar will be called LLK grammar and this is the parser will be called LLK parser. So, there is a rule which says that this a grammar G is LL1 if and only if whenever A producing alpha or beta are two distinct productions of G, the following conditions will hold. For no terminal A do alpha and beta both derive strings beginning with A. So, it should not be that for both of them. So, if you think about the strings which are derivable from alpha, alpha is a string of terminals and non-terminals. So, if you derive further strings from alpha, so it suppose it starts with a symbol A, the string starts with a symbol A. So, with beta if I do the same thing, it should not be the case that with beta also I can come to a situation where the derived string starts with A. Naturally, in that case there will be confusion. So, if you look into the first of alpha and first of beta, if both of them contains A, so you cannot decide that whether on getting A whether you should follow the production A producing alpha or the production A producing beta. So, that is one thing. Second point is that at most one of alpha or beta can derive empty string. So, that is epsilon production. So, that is also there, like if, if you find that at some point of time I need to consume entire capital A in my sentential form without consuming any further input. So, I should try to replace it by alpha, where alpha can give me epsilon, or beta if beta can give me epsilon, but it should not happen that both alpha and beta can give epsilon. So, at most one of them can give epsilon. So, then we do not have any problem of choice, otherwise there is a choice. So, I can either produce by A producing alpha or A producing beta. So, I really do not know which one will be correct. So, that can lead to some erroneous action by the parser. And if A in if alpha in a number of steps produces epsilon, then beta does not derive any string beginning with a terminal in the follow of A. So, this is another condition. So, it says that if so I have got some string that put at this place I have got A and then I have got something else. Now, I have got a choice, I can replace A by alpha or A by beta. So, if I replace A by alpha, and alpha can give me epsilon, alpha can give me epsilon, then from beta I should not be able to derive any string that has got with a terminal in follow of A. So, that is this so if I could have gone with beta and it can give me a valid string where there is a symbol which is in follow of B that can come, say B is in follow of capital A. So, that can come. So, then there will be confusion again. So, these are the three conditions that that are to be satisfied for a grammar to be LL1. So, the detailed proof can be obtained in some in some formal language theory book, but we are not looking into that. So, we will be following these rules to determine whether a grammar is LL1 or not. Even without doing these checks, so you can decide like whether a grammar is LL1 or not by constructing the corresponding parsing table, and if the grammar is not LL1, then there will be multiple entries in the parsing table for a particular value. So, naturally whenever there are multiple values at some entries, so we have got we say that there is a the grammar has got problem. So, it is not LL1 grammar. So, we will see that. So, how do you construct a predictive parsing table? So, what the predictive parsing strategy will do is that it will have a parsing table. So, like this. So, it will have a parsing table, and looking into the grammar symbol that is there on some stack and the next input symbol. So, it will decide like what action to take. So, if the stack top contains E and the next input symbol is ID, then this table says that you go by this rule, E producing T E dash. So, it will go by this rule. Okay. So, I think there is a so we will see how to construct this parsing table. So, for each production A producing alpha in the grammar, so we do like this. For each terminal A in first of alpha, we add A producing alpha in the table A. So, this table is two dimensional table. In one dimension we have got all the non terminals. So, this is the table M. So, here I have got all the non terminals from the set Vn, this set I have got all the terminals. Okay. So, that way, so this MAA is corresponding to this particular non terminal and this particular terminal. So, what is the entry here? So, that entry is decided by this. So, if A is in first of alpha, where if A producing alpha is a rule, if A producing alpha is a grammar rule and first of alpha contains A, then we add this rule A producing alpha to this particular entry. Then it says that if epsilon is in first of alpha, then for each terminal B in follow of A, we add A producing alpha to the table MAB. So, if epsilon is in first of alpha, so this can give me epsilon, then we for every terminal which can give me follow of A, which is there in follow of A. So, I will like to reduce this by epsilon. So, this will be added to MAB, and finally, if epsilon is in first of alpha and dollar is in follow of A, then we add A producing alpha to MA dollar as well. And after doing this, whatever entries are undefined, we mark them as error entry. So, how does it so if I look into the example, like say how is it constituted? So, this is the grammar rules that we have, ETF grammar modified by eliminating left recursion and all, and this is the first and follow sets that we have computed. Now, let us look into this rule, E producing T E dash. Now, as far as our rule is concerned, so it says that if A producing alpha, so we have to see the first of alpha. So, first of alpha, first of T E dash is equal to first of T. So, it is bracket start and ID. Okay. So, in bracket start and ID we add this rule. So, E producing T E dash is added here and here, fine. Then then we have to have this whether this first of t dash first of t dash contains epsilon or not, that has to be seen. So, as for the second rule, it says that if epsilon is in first of alpha, so whether epsilon is in first of alpha or not, so that has to be seen. So, first of t dash, so first of t does not contain epsilon, so there is no question of first of t dash containing epsilon. So, second rule is not necessary. Now, come to the rule E dash producing plus T E dash. So, first of plus T E dash is plus. So, I will add this rule E dash producing plus T E dash in this particular entry. Now look into this rule E dash producing epsilon. So, by that second rule it says that whenever I have got epsilon A producing epsilon, then whatever we have in the follow of A, there I should add this particular rule. So, follow of E dash, so follow of E dash is bracket close and dollar. So, E dash bracket close I have added E dash producing epsilon, and dollar I have given E dash producing epsilon. So, this is added to these two rules. Then this next coming to this rule T producing F T dash. So, F T dash, first of F T dash will is equal to first of F, that is bracket start and I D. So, bracket I D and bracket start. So, we have added this T producing F T dash. Now comes T dash producing star F T dash. So, by the similar rule like T dash produces star. So, the first of this star F T dash is equal to star. So, at T dash star, so we add this particular rule T dash produces start F T dash, and then T dash produces epsilon. So, whatever we have in the follow of T dash plus bracket close and dollar. So, there I will add T dash producing epsilon. So, plus bracket close and dollar we have added T dash producing epsilon. Then finally, so this particular rule F producing within bracket E. So, first of this contains bracket start. So, F bracket start is F producing within bracket E, and this I D. So, this I D part is this is applying the other rules F producing I D. So, first of this part is I D only. So, this F I D. So, we have added this thing. So, the simple rule is wherever you have got the first. So, look into the first set, and whatever symbols are coming in the first set. So, you add the rules at those points, and if the first produces epsilon, then whatever is in the follow of the non-terminal, then for all of them we add the rule. So, that is the straightaway rule. So, for producing the predictive parsing table. So, we will see how can we use it for this parsing job. Now, we can produce the other entries, like all these entries which are left as blank. So, they are actually error entries. So, error entry means so if you have got non-terminal E and the next input symbol is plus. So, on E you cannot get a plus. Okay. So, this is an error. So, all these entries that we have here, so they can be marked as error. They can be marked as error. So, whenever the parser comes to these states, this particular table entry, okay, so that means there is an error in the input stream. As a result, it has come to this. So, the input stream has to be rejected, it is not there is some syntax error, and the parser needs to recover, so that it can continue parsing with the remaining strings.